All right, this looks epic, doesn't it? We've got Edgar trying to get from O to B, running along the edge of the marsh, a distance x, and it says the he's running at lambda meters per second. So I'm just going to write that the distance is this, and v is equal to lambda, and then wades through the marsh at 1 meters per second. So here v is equal to 1. I'm going to work out the distance. This distance here is going to be like the whole thing is a and this part is x, so this is going to be a minus x, which means that this distance is going to be, we're going to use Pythagoras' theorem, a minus x squared plus b squared square rooted. And the point at which Edgar is going to start wading through the marsh is going to depend on lambda. Because if lambda was like really large, for example, then it's going to make sense to run the whole way around the marsh. You know, if it was like 100 or something. But if lambda is much smaller, like 1.1, it's just a bit bigger, then it's going to make sense to actually start wading through the marsh like more quickly. In fact, it's probably between those two values, and there's, but basically this is an optimization problem. What's the best route to take given given what lambda is? Now we're asked to find an expression in terms of x for the time taken for Edgar to reach B from O. So here we've got distance as x, we've got v is equal to lambda. Remember, speed is equal to distance over time, which we can rearrange to time equaling distance over speed. And so the overall time is going to be the time taken to run along the edge of the marsh, which is going to be x over lambda, plus the time taken to wade through the marsh, which is then going to be a minus x squared plus b squared divided by 1. So there we have it, we've got the time. And from this, we need to show that dt by dx is equal to this quantity here. So dt by dx, actually, maybe before I do that, because I'm going to be differentiating with respect to x, I'm just going to rewrite it. Let me write it as 1 over lambda x plus a minus x squared plus b squared, all raised to the power of a half. Then dt by dx is going to equal 1 over lambda plus, now I need to use the chain rule. I'm going to times through by a half, that's my power. Then I'm going to times through by the derivative of the inside, which is going to be 2 a minus x. But I've actually then got to think about the minus x, so I'm going to then times by minus 1. Let me just move this up here. Okay, so I'm timesing by the half, I'm timesing by the derivative of the inside, which the constant I don't get anything from, but I'm going to times by the derivative of this, which is 2 times a minus x. I just then need to times by minus 1, and then I'm going to times by all of this, but with the power reduced. So it's going to be to the minus a half. Kind of run out of space here, I'm trying to cram it all in. So then I'm going to get 1 over lambda, and then these are going to cancel. So it's going to be minus a minus x, because of the minus 1, and then I'm dividing by this. Yeah, which is exactly the same as what is given. So that bit is sorted. Good start. Next, we're asked to find in terms of a, b, and lambda the value of x for which dt by dx is equal to 0. So got dt by dx. Therefore, I just need to set it equal to 0. 1 minus 1 over lambda minus a minus x over a minus x squared plus b squared is equal to 0. I'm going to just rearrange that, add this to both sides, and actually it's going to be that these two are equal to one another. And then I can multiply through by this denominator, and actually I probably times through by lambda. There we go. Next, I'm going to square both sides. Remember, I'm trying to get x in terms of the other things. Square both sides, that's going to give a minus x squared plus b squared is equal to lambda squared a minus x squared. Now, if I minus a minus x squared from both sides, I get b squared is equal to lambda squared a minus x squared minus a minus x squared. And there's a common factor of a minus x squared. I can actually factorize that out. I'm going to get lambda squared minus 1 times a minus x squared. Therefore, a minus x squared is going to equal b squared over lambda squared minus 1. This is a bit like when you complete the square, you try and get, the x by itself somehow, and then you just, but I've got a squared here. I don't want to get rid of that yet. I don't want to like expand it out or anything. But now we're in a position where we can square root both sides. So a minus x is going to equal the square root of b squared over lambda squared minus 1, plus or minus because we're taking that square root. And I can rearrange this. I can add x to both sides and then minus or plus this to both sides. I'm going to get that x is equal to a plus or minus the square root of b squared over lambda squared minus 1. I could have swapped it around to minus plus, but that's actually not going to make any difference. So I've just kept it exactly the same. So I hope you're happy with that. Now, right at the start of the question, I didn't spend time talking about all these things. Where are we here? We were told that actually x is between 0 and a, because you're not going to go beyond and then start going that way. So it can't, yeah, actually it's got to be less than a. X less than a, so reject the plus solution because it would then be more, and therefore x is equal to a minus the square root of b squared over lambda squared minus 1. Nice. So we've got the value of x in terms of a, b, and lambda. Next, it says show this value of x lies in the interval 0 less than or equal to x less than a, provided that lambda is greater or equal to this. So if 0 is less than or equal to x, which is less than a, actually, we've already checked this. in part one. So I can ignore that part. This is satisfied. Just this part here. Then I can just focus on x being greater or equal to 0. So a minus the square root of b squared over lambda squared minus 1 is greater or equal to 0. And now I need to rearrange this to make lambda squared the subject. So a is going to be greater or equal to b squared over lambda squared minus 1. Now I can square both sides here. You've got to be really careful when you have inequalities. So a greater than 0 and the square root of b squared over lambda squared minus 1 is greater than 0. So we can square both sides. If one was negative, it becomes more problematic. A squared is greater or equal to b squared over lambda squared minus 1. And also lambda squared minus 1 is greater than 0 because lambda is greater than 1. That's what it said at the start of the question. So we can multiply through by that. Lambda squared minus 1 times a squared is greater or equal to b squared. Lambda squared a squared minus a squared is greater or equal to b squared. So lambda squared is going to be greater or equal to, how they're written in the answer, 1 plus b squared over a squared. Okay, b squared plus a squared divided by a squared. That's going to be 1 plus b squared over a squared. I just sort of swap these two around, divided by a squared. And again, everything's going to be positive here. So we can square root. Lambda is going to be greater or equal to the square root of 1 plus b squared over a squared. Okay, good so far. I just want to take a little recap of where we are. So we've got this situation with the marshland running through the marshland, then across the marsh. We've we've got the time that it takes to do this, and then we've looked at finding a derivative of that, setting it equal to 0 to get the value of x for which that will occur, i.e. the optimal, given a value of lambda, where should we start crossing? We've shown that it's going to be between 0 and a, provided that lambda is greater or equal to this value here. Um, those are the conditions we have. And then for lambda in this range, okay, now we're on part 3. We need to show that this value of x gives the minimum time. Okay, because we know it's a stationary point, but we don't actually know that it's the minimum, so we're being asked to show this. So let's return to the derivative of t with respect to x, and we're asked to show that it gets a minimum value of t. I'm just going to tidy this up for a second, then we're going to look at the second derivative. But in this case, I don't want to write it like as divided by root. I want to keep it in power form. That's why I've rewritten it. Okay, so we can differentiate with x with respect to x again. Now that 1 over lambda is just going to disappear, I'm going to need to use the products rule on the rest of it. So let me treat it as these two separate functions. So first of all, I'm going to times by the derivative of this, which is actually just going to be 1. I mean, if I expanded it out, I'd get x minus a. So I'm going to get a minus x squared plus b squared all to the power minus a half. And then it's going to be plus this thing, which is going to be minus a minus x. And I'm going to times by the derivative of this function. So it's going to be minus a half, bring the power down, times by the derivative of this, which is going to be 2 times a minus x. And then I have to times by the derivative of the minus x. I'm going to get a minus 1. And then I'll have a minus x squared plus b squared minus 1 from the power. So it's all to minus 3 over 2. And let's just tidy this up. So we want to show that it is, for it to be a minimum, we need to show that it's greater than 0 when we get x equals, what was it? X was this thing here. Okay, so I'll be substituting that in a minute. Just leave that down here for the moment. Right, so I'm just going to make this a little bit tidier. I can write it as 1 over the square root of a minus x squared plus b squared. Right, I'll be just be careful here. I've got a 2.5, which are going to cancel. I've got a minus 1 and a minus that are going to cancel. I'm still going to be left with a negative. So it's going to become minus a minus x squared, because I'm timesing those two together, divided by, okay, because there's a negative, a minus x squared plus b squared. Maybe I should leave it as to the power of 3 over 2. Oh, okay, I've done. I might come back to that. This thing here, this is all raised to the power of 3. And now I'm going to substitute in x. So when that is true, I'm going to get the a minus x. I think it's because that is appearing in 3 times. It's worth working out what that is. That is going to be the square root of b squared over lambda squared minus 1. And the second derivative is then going to equal 1 over the square root. And I can substitute in now, so I'm going to get b squared over lambda squared minus 1, because I'm squaring it, aren't I? I've got a minus x squared plus b squared minus, I don't know if I've got enough room, so I'll go down to the next line. Okay, yeah. Again, I want to show this is greater than equal to greater than 0. Still a bit to do. I can put this over a common denominator, in fact, so I can write b squared as b squared over lambda squared minus 1, and then times by lambda squared minus 1. And I can do the same over here. because then what's going to happen? I'm going to get 1 over the square root. It's going to be b squared plus b squared lambda squared minus b squared. So these two are actually going to cancel. And same over here as well. This is going to cancel with this. Okay, I could cube the whole thing or I can cube it after. I might just cube it after for the time being. Yeah, we're getting there, I promise. So I can take this, I can actually, because I'm basically dividing, I've got a 1 divided by a fraction and I've got the square root in there, but I can flip that around. It's going to be lambda squared minus 1 over b squared lambda squared, all square rooted, minus b squared over lambda squared minus 1. I can flip this one around as well. Lambda squared minus 1 over b squared lambda squared square rooted all to power 3. So then I'm going to get square root of lambda squared minus 1 divided by, I can actually take the square root to the bottom, b lambda and then I'm going to get square root lambda squared minus 1 divided by b lambda all cubed. Yeah, I'm going to bring these fractions together now. That's going to be important. So I'm going to actually cube this, which means that I can write it as b cubed, h cubed on the bottom, get rid of that. And then it's going to be this cubed, which is the same as having lambda squared minus 1 times, sorry, rooted times lambda squared minus 1. That's the same as having lambda squared minus 1 rooted cubed. And that will cancel with that. And the b squared will cancel with the b cubed. So I need to get it over a common denominator now. It's going to be lambda squared minus 1 over b lambda cubed minus lambda squared minus 1 over b lambda cubed, which will be lambda squared minus 1 times lambda squared minus 1 rooted divided by b lambda cubed. Now remember, lambda is greater than 1, so this is necessarily going to be greater than 0. Hence, x equals, and I can't remember what it is at this point. Is a minimum. Good. No. So, to be fair, that took me a lot of effort. And if you look at the work salute, like the mark scheme, they do it really, they do it much quicker. So I'm going to talk about it briefly. I didn't think to do this. So they find the second derivative, they write it as minus n over d, where d is this, which we got, and then n is this. And then they manage to rearrange it pretty quickly into this form. So they don't even substitute in for x, but basically they just, they cancel these two out, and then they justify that this is going to be positive and this is going to be positive. So I have taken a long route through this, and it was unnecessary. It's just I'm just kind of telling you the way I did it, and it's I didn't think it was obvious to do what they did, but maybe you're happy with that instead. But in any case, where are we with this problem? We've done all of this, and now we've shown for lambda in this range that we do get a minimum, the value of x. See, it even kind of implies putting the value of x in, that's normally what you do, but actually you can get away without doing that. It will necessarily be positive. Okay, part C, find the minimum time taken for Edgar to get from O to B in these two situations. Now, when lambda is big enough, and as we saw earlier on, then we're going to run along the edge of the marsh for a little bit, or Edgar is, and then diagonally. So we can use that. I just want to quickly talk about part two, because that's going to come into it. What happens when lambda becomes too small? Okay, it's still greater than 1, but now it's smaller than this. Well, what is actually going to happen is that Edgar's going to just going to run straight across the marshland at this point. There's no advantage to running a longer distance because lambda is not large enough. So it's just going to be a diagonal. Okay, let's take a look at these two situations. Okay, well, we have the time taken. Right, this is situation number 1. So the time taken is this, and we know that this value of x gives a minimum time. So t is going to be 1 over lambda times a minus the square root b squared over lambda squared minus 1 plus, I've got this thing here. Remember we've already dealt with this earlier actually, haven't we? This a minus x. I'm just going to do it again. It's going to be b squared over lambda squared minus 1. That's going to be my a minus x all squared plus b squared square rooted. Now I can write this as divided by lambda squared minus 1 times it by lambda squared minus 1 like before, and then this is going to cancel out with that minus 1 there. I might just expand this actually, this bracket. Here I'm going to get b over lambda squared minus 1. And then over here, I'm also going to get, when I square root it, I'm going to get b lambda over root lambda squared minus 1. I'm going to put this over a common denominator of lambda. I'll just take it out actually. 1 over lambda. Sorry, I'm gonna bring it. I expanded it, but now I want to bring it back together. So it's going to be a minus b. I mean, we've got the answer. We just need to tidy it up a little bit. And then this is going to become b lambda squared. And then I'm going to get a plus b lambda squared minus b. Now, because it's a minus b, I can actually factorize it out, and I could write it like this. And then my final answer, if I want to make it as simple as possible, I can divide, this is just lambda squared minus 1 square rooted squared. So I can then cancel that out. Let me just explain a bit more. So I could write this as this squared. So I'm going to get a plus b times root lambda squared minus 1 all over lambda. If you don't quite get to that simplified answer, don't stress too much, but it's good to see here. Now on to part 2, where lambda is between these values here. So as I was saying before, what you have to realize is like we had that condition before, didn't we? When lambda was greater, sorry, it was ages ago we did this. Here we go. The x will lie in the interval 0 to a, provided that lambda is greater or equal to this. So now it's not, it's actually going to be less. And we can think about this physically. Like I know I talked about it before, I just want to talk about it again. So when it becomes sufficiently small, it's just going to be best to simply wade through the swamp from the very start. So in fact, we're going to be going along this diagonal. And we're just going to get a squared plus b squared square rooted. So that's my distance. V is equal to 1. And so the time is just this divided by this, which simply gives me a squared plus b squared square rooted as my time. Okay, we've got one more part of this question, believe it or not. We're not done yet. Edgar's friend Frankie also runs at a constant speed of lambda the whole way, and Frankie runs along the edges OA and AB. And we're given that lambda is greater or equal to this. So the distance traveled by Frankie is simply going to be a plus b, and the speed is lambda, so the time will be a plus b over lambda. Just want to make one point. Remember, Edgar is also running at this speed, lambda, but in his case, he has to wade through the marsh at some point. That's why even though they're running at the same speed, at some point, because Edgar has to wade through the marsh, Frankie might end up going faster. Even though it's Edgar's minimum time, the minimum time is forced about by like going through the marsh, and it could be, in fact, that it would have been better to have gone the way that Frankie's going, but there's a restriction there, so we can't do that. So we have this time, and then remember we've got the minimum time of Edgar from before. Here it is. And this is why it's going to be really useful to have it in a simplified form. So this is Edgar from C part 1. Now remember, we're interested in the range of values of lambda, which Frankie gets to B from O in a shorter time than Edgar's minimum time. So we're interested in A plus B over lambda being less than A plus B square root lambda squared minus 1 over lambda. Now this question itself, like once you've got that, is not difficult, but it is so easy to have made a mistake at some point in this question. Up to this point, we've done so many steps, so chances are that a mistake would have been made, and especially under time conditions. But this is it now, and we can actually times through by lambda, We can then minus a from both sides. I'll just put that intermediate step in. Then divide through by b. Both of these are positive. Lambda is still greater than 1. So we can actually square both sides now. So it's going to be lambda squared minus 1 is greater than 1, which means lambda squared is greater than 2. Now again, lambda is necessarily positive, so I can just take the square roots. Don't have to think about any negative coming out. And lambda is going to be greater than root 2. Frankie will get from O to B more quickly when lambda is greater than root 2. Edgar must wade through the marsh at some point. Oh, okay, well done for last in this video. I hope it all makes sense, and give yourself some credit for having hopefully understood this question. A tough question and very, very, very long question at the end of this advanced extension award paper.